It's nice to be here in Ahmedabad, and I'd like to thank the School of Arts and Sciences, particularly Manjil, for the kind invitation. Though this is my second trip, last time I was here just for one day. This time I go to explore a lot more, thanks to my friend Dr. Sital Patel. And anyway, so today I'm going to talk about some interesting problem in number theory. The problem looks very simple, looks very elementary, but of course it's easy to state. But however, we can't say the same thing about the proofs or the results. But let me start with this work on squares in arithmetic progression. So, okay, I have this one simple problem. So find all arithmetic progressions which are squares, right? You have this arithmetic progression n plus d, n plus 2d, n plus 3d, and so on. And you want all of them to be squares. So the first term n, of course, so here is the length k arithmetic progression. K can be, of course, it doesn't make sense to have one arithmetic, I mean, when k is 1, we have nothing to do. So we started at least 2 term AP, which is n plus d. So now when, in case of 2, we're looking for 2 term arithmetic progression, both of which are squares, then clearly you can have infinitely many arithmetic progressions of length 2 which are squares. So n is a square, n plus d is b square. So this is always possible. Now if you look at 3 term arithmetic progressions of all squares, then also we can easily say, like, if you take, in fact, you have infinitely many families, and one such family is given by taking any 2 integers r and s of opposite parity. Opposite parity means one is odd, other even. So if r is odd, s is even, and vice versa. You take r is bigger than s, and you take this r and s to be co-prime. Basically, when I look at arithmetic progressions, I'm looking at the arithmetic progressions which are pairwise, like the leading term and common difference is co-prime. So now you take the number n to be r square minus s square minus 2rs square, and d to be 4rs times r square minus s square. Clearly, you can see that n is this number. Of course, n is already a square, nothing to do here. If you add n plus d by it's a simple algebraic manipulation, you can easily show that this is r square plus s square whole square. Now n plus 2d is r square minus s square plus 2rs whole square. So basically, you can have infinitely many 3 term AP by so r and s can be, you choose any 2 numbers r and s of different parity, r bigger than s, they're co-prime, and you just have this. So you have infinitely many 3 term arithmetic progressions which are all squares. So 4, 2 is infinitely 3 infinity. Now let's go to 4. So can you continue this? That's the question. Now the buck stops here at 4. So Fermat, of course, the well-known number theorist Pierre de Fermat, who is also known for Fermat's last term. So he proved that for any n and d, you cannot have 4 terms, consecutive terms which are all squares. So you cannot have n square, n plus 2d square, n plus 3d, n plus 4d, n plus 3d. This all of them, you cannot have 4 term AP which are all squares. Now, of course, Euler comes in picture. Euler is famous of course, many of these well-known results in number theory. So in particular, he generalized a lot of Fermat's results. So in this particular case also, he generalized this result of Fermat by saying that not only you cannot write product of 4, you cannot have 4 squares in arithmetic progression, you cannot have product of 4 consecutive terms can never be a square. So n plus d, n plus 2d, n plus 3d cannot be a square. So once 4 is not possible, then you can go, I mean, anything bigger than 4 is not possible. So now, obviously, 2 important questions come up. The first question is that, so Euler says that you have product of 4 consecutive terms of AP cannot be a square. So the next question is that, can you have a product of 5 or, I mean, so I should have written 5 or more, but 4 or more terms. So can a product of 5 consecutive times is 6 consecutive terms, or any given, say, any number, any k consecutive terms is a square. The second problem which can occur is that take any arithmetic progression of length n, how many squares can we expect? So these two are two important questions coming from that one. Now I'll first consider the first question. So, so here I want to state a result of mine with Hirata Kono, Soren Tideman, which we proved in 2006. So we sort of generalize the result of Euler by showing that if you have not only 4, but if you have 5, 6, 7, up to 109 terms, then k, if you take any k between 4 and 109, then product of k consecutive terms of an arithmetic progression can never be a square. So yeah, so basically, also the problem is that we want to show that product of any k consecutive, any number of consecutive terms is not a square, but we went up to 109. Here, independently, there's a result of Bennett, Bruin, Giori, and Haidu. They proved that product of 5, 6, 7, or 8, up to 11 terms cannot be a square. So our approaches are a bit different, but we went all the way up to 109. Okay, so I'll come to that. So definitely that's the question I was expecting someone to ask. So we proved there's something more general result for up to 100. And as a byproduct, we went up to 109. So basically, I'm going to come to the next slides where we have a result where we went something more general result up to 100. From 100 as a byproduct, I get 109. So I'll come to that. So our theorem 1 gives a partial answer to the following open problem. Product of, if you take product of, the conjecture is that product of 4 or more consecutive terms of arithmetic progression is never a square. That is the open problem, this open conjecture. So our result gives a partial answer by saying that you can have up to 109 terms. Beyond 109, we don't know how to do it for all, but up to 109, you don't expect, the conjecture is true. Now, about the question how 109 was coming, actually, this has to do with the general problem. So I'm going to define some notations. This one I'm going to also tell you later on what does this means. Just for the sake of simplicity, take any n and d, k with n and d, GCD 1, co-prime, and k be an integer. And so you want to write delta of n d k is just nothing but the product of k consecutive terms of arithmetic progression starting at n. n plus d, n plus 2 d up to n plus k minus 1 d. And for me, p is not a polynomial, or p of some number is just a maximal prime divisor. For example, p of 100 is 5 because 2 and 5 are the only primes dividing 100. And for completeness, we take p of 1 to be 1. And omega of some number is nothing but the number of distinct prime divisors. 100 has 2 and 5 has 2 prime divisors, so omega of 100 is 2. And omega of 1 is not equal to any prime, so omega of 1 is 0. This is just later on, so whenever I'll just going to tell you. So we started with a very simple observation, which we learned in high school, and in fact, otherwise, if you high school and beyond, is that if you have a product of k consecutive integers, is divisible by k factorial. Like binomial coefficient n choose k is always integer. That tells you that k factorial divides product of k consecutive integers. Now you can also easily show that if you have a product of k consecutive terms of an arithmetic progression, then if you take any prime less than k, so basically k factorial divides a product of k consecutive integer is saying that any prime divisor less than or equal to k divides a product of k consecutive integers. You can generalize by showing that if you take a product of k consecutive integers, any prime less than or equal to k will divide. Now I've taken n and d to be co-prime, so any prime dividing d will not divide the product. So, but if you take any prime which doesn't divide the n less than or equal to k, it will divide the product. Therefore, the largest prime factor of a product of k consecutive integers is always going to be bigger than the largest prime divisor less than or equal to k, which are co-prime to d. So pi of dk, I call P1 to be 2, P2 to be 3, and so on, the set of sequence of primes. And pi of k is the number of primes up to k. And pi of dk is the number of primes less than k such that p doesn't divide d. So basically, every prime less than or equal to k divides this number. Every prime less than or equal to k which doesn't divide d divides this number. So largest prime factor is very close to k. I mean, no bigger than or equal to a prime which is at most k. I mean, I'm not saying that this is the best possible, but we have this result. So here two obvious questions can come up. The first problem is that can you have a prime bigger than k dividing this product? So that's the first question. Every prime less than k co-prime to d, or which doesn't divide d divides it. Now, can I have a prime bigger than k? The second problem is that can I have a prime bigger than k such that which divides the product with the power odd. So P power L exactly, this symbols for exactly divide. So P power L divides this product, but P power L plus 1 doesn't divide this product. So can you find a prime bigger than k which divides this product, but the exact power of P dividing is odd? So these two are questions which I can ask. I know that every prime less than k divides. Fine. So what about primes bigger than k? Or can you find a question number 2 is a more difficult problem than one. It says that I'm looking for a prime which divides to an odd power. So let's start with the question number 2. What the question number 2 says is that can you find a prime bigger than k which divides this product of k consecutive terms of an arithmetic progression to an odd power? Suppose the answer is no. What happened? Then every prime bigger than k will divide this product to an even power. So that means order of prime p, the power of p dividing this product is going to be 0 mod 2. Now, therefore, if you write this number as square part and square part and square free part, every prime dividing the, so you can always write a number as square free times a square part, right? Now, any prime bigger than k will divide to a square part, so it will go divide y. So b will be a number, so you can write this as product of b times square where b is square free. Square free means a number which is not divisible by any power of any prime. For example, say 3, 5, 10, 15. These are the numbers where square of any prime doesn't divide. And not only that, what we are asking is that the largest prime factor of b is less than or equal to k. So to answer this problem, I want to show. So if this is not true, then we have an equation of this form. So this can be written as b times y square, where b is a square free number whose largest prime factor is less than or equal to k. So we need to consider this equation. Now, first, let's see what happens when these one, we're going to consider this. When these one, the equation is nothing but a product of k consecutive, this is a product of k consecutive integers is some b times y square, where b is a number which is square free and largest prime factor is less than or equal to k. So this equation has been completely solved from the work of Erdős, Righe, Erdős, Selfridge, and Sarda. Basically, Erdős and Righe first had some partial result, then Erdős and Selfridge completely proved it so that there are no solutions to this. And later on, Sarda extended with b equal to 1. Later on, Sarda extended with b bigger than 1. So I won't go much into history, but this is their work. So that's why we're going to consider this equation with d bigger than 1. So basically, we're going to consider this equation with d bigger than 1. So maybe I'm going to write that equation to be. n plus d, n plus k minus 1 d equal to by square, b square free. So largest prime factor, p of b less than or equal to k. So this is the equation we're considering. So here, when k is 4, so what is k? So when k is 4, you are looking at 4, n plus t, n plus 2d, n plus 3d is either 1. So b is a number which is square free, largest prime factor is less than or equal to 4. So primes less than or equal to 4 are 2 and 3. So numbers which are square free composed of 2 and 3. So either 1, 2, 3 or 6. So we're looking at this equation with b coming from 1, 2, 3, 6. So here we're going to show that when b is 1, 2 or 3, there are no solutions. When b is 6, there are infinitely many solutions. So I just want to introduce, Euler gave a proof of the fact that when b is 1, there are no solutions, but we are going to give a different proof by by converting it to an elliptic curve. Suppose this equation has a solution. Now you divide by n power 4 on both sides. So then it becomes 1 plus d by n, 1 plus 2d by n, 1 plus 3d by n is by square by n power 4. Now you sort of make a complete square by multiplying 2b here, 3b here, and 6b here. Why you are doing is that if you multiply by 2b here, it's going to be 6bd by n, 3b 6bd by n, 6bd by n. So, and you get something, you see b is fixed, 1, 2, 3, 6, so you can multiply. So it becomes 6b square, so 6b cubed. So 6b, 3b, and 3b. So y. Yeah, right. And earlier you have b, only you have b here. With all of them, you put it together, you get 6b square y by n square whole square becomes this. So this is the equation we have. Now you put this number as capital X, this number is capital Y. Then you obtain this curve, y square is x times x plus b, x plus 4b, where x and y are rational numbers. So this is a curve. Then it turns out that this is an elliptic curve. So elliptic curves are curves of the form y square equal to fx, where f is a cubic whose discriminant is non-zero. And and this is well studied. Elliptic curves, they satisfy certain property that either, so it has something called, the points on elliptic curve, they satisfy, they have something called torsion points, points of finite order and infinite order. So we have such reasons. I won't go much into it. Basically, once it becomes an elliptic curve, then it turns out that the rank, this curve has rank 0. So if the rank is positive, it has infinitely many rational points. Now rank is 0 means it has only finally many rational points. So when b is 1, 2, 3, its rank is 0. When b is 6, its rank is 1. So when b is 0, when b is 1, 2, 3, rank is 0 means it has only finally many rational points. And from the finally many rational points, you don't get any integer points to the original equation. But we can't say the same thing for b equal to 6. I'll come to that. So when b is not equal to 6, when b is 1, 2, 3, you have only finally many rational points. And by going back, you find that there are no solutions to the original, this equation with k equal to 4, b is 1, 2, 3. So now what happens that when k is 4, b equal to 6? So here we're going to show that there are infinitely many solutions to this equation. So, so the way I'm using is a nice idea called Runge's method. So basically you start with a solution, then generate another solution and keep on generating so that there are infinitely many solutions. First, you see that when n is 1, this one, there's a solution. 1, 2, 3, 4 is 24. 24 is 6 times 2 square. So there's a solution when n is 1, d is 1. So Yeah, so anyway, where the solution? So we start with any solution n naught, d naught, y naught, which satisfies this. Now take x naught to be, n naught by d naught, y naught to be 6 y naught by d square. Then if you multiply by 6 on both sides and divide by d to the power 4, 1, 2, 3, 4. Yeah, so then this n naught by d naught, y naught, or 6 y naught by d naught square is a solution of this equation. Now this is a curve y square equal to of degree 4 where x and y are rational numbers. There are no more integers. Now you put, capital X to be some x plus x naught. You see x naught is given to us. With x naught equal to 0, you substitute here and get a new equation which is g square is 6 times x plus x naught, or x plus x naught plus 1 and so on, which you write in this form, which is some a naught x power 4, a1 x cube, a2x square, a3x plus a4, where when x is 0, so a4 is nothing but y naught square. So it has a solution when x is 0, small g is y naught. So it's a solution. This is what I get. It has one solution. So what I'm going to do is that I'm going to take a and b given by 2y naught a plus b square is a2, 2y naught b is equal to a3. So I know what is small a, small a1, a2, a3, a4. So I know capital Y naught. So I'm going to find a and b satisfying this property. From here I get b, which is a3 by 2y naught. And from here I get a. Then it turns out that small x is a1 minus 2b by a square minus a naught. G is ax square plus bx plus y naught is a solution of this equation. So this implies that x plus x naught, which is a1 minus 2ab by a square minus a naught plus x naught is a new value of x satisfying our original equation. And from here, you can get back, okay, so you remember that x is n by d, y naught is 6y by d square. So you can get back new solution of the original equation. Okay, so this one. Yeah, these are coefficients. So from here, you make a new equation where a naught, a1, a2, a3, a4 are given. So you get a new value of solution. So basically, you start with x capital X naught, y naught, you get a solution of this new equation. So I do the same thing with this. I start with n equal to d equal to 1, y equal to 2. You get a new solution 6769071. Y. That's another next solution, which is actually quite big. So now I can start with this. I'll get another solution, and we can show easily that this n and d keep on increasing, so that this doesn't stop. So this tells you that this equation has infinitely many solutions. Yeah, of course. Yeah. Yes, please.
Yeah, so when we have the elliptic curve, right?
Yes.
So if you take just one point and keep on adding,
you
generate new one.
No, so the thing is that, okay, yes. So for this, when b is 1, 2, 3, the rank is 0. So I say only points are only finitely many. That's fine. When b equal to 6, yeah, it has. So it has infinite. Like rank is 1, so it has infinite many points. So that is one way to see. But then from that, going back to the original solution is not that easy. So this is a easier way to generate solutions. That will also tell you that there are infinitely many rational solutions. But our point is so that there are infinitely many integer solutions. So there's a result of Ziegel called. So given any elliptic curve, there are only finitely many integer points. There can be infinitely many rational points, but finitely many rational integer points. So, but many rational solution can give the same integer point. That's the problem. So there's a result of Mazur and so on that I mean, of course, the Ziegel's theorem says that there are only finitely many, I mean, given any curve whose genus is positive, it has only finitely many integral points. So when I look at this equation, this elliptic curve, though it may have infinitely many rational points, but only finitely many integer points. So x, yeah, so that cannot exactly give this, say that for b equal to 6, there are only finitely many integer points to the integer solutions. That's why we have to employ a new method. Okay, so yeah, it's a kind of, I mean, yeah, that's what initially people think, but I mean, like, people think that why can't we do the same thing, but it's because of the theory and how it works, it doesn't, I mean, so they have to employ a new method. Okay, all right, so yeah, so this is called Runge's method, where from one you keep on solving, keep on getting a new solution. So because of this, the conjecture, so the for I mean, there are no solutions, then the general conjecture is that this equation has no positive integer here. So positive integer solutions n, d, k, b, y with k at least 5. Largest prime factor of b less than or equal to k, where b is a square-free number. There are no solutions of this equation. So this is the conjecture. Because k equal to 4, there are no, I mean, for b equal to 6, there are infinitely many solutions. And when people look at this expected, so it is expected that when k, the number of terms is at least 5, then there are no solutions. This is an open problem. So the original problem was with b equal to 1. Okay, so now I'll come to your earlier question about 109. So this equation has no solution when k is from 5 to 100. So where b is any number with largest prime factor less than or equal to k, and b is a square-free number. This has no solution. The conjecture is that for any k bigger than or equal to 5, there are no solutions. But we could go up to 100. Here, the case k equal to 6 is due to Bennett, Bruin, Jory, and Haidu. And by a different, I mean, so, and for k all the way up to 100 with k different from 6 is due to us. And I mean, there are some few cases left which Sabox Tenge he completed. So for, I mean, if you take 5, 6, 7, or all the way up to 100 consecutive, I mean, for any k with k consecutive terms, it's not only square, but cannot be square times, almost a square times a number whose square-free number whose largest prime factor is less than or equal to k. And from here in b equal to 1, with some arguments, I can extend 100 to 109. That was the original result I had. Okay, so this is one result on the direction of the conjecture. The conjecture is still open, but we can say a little bit more. We can say that, like, if d is larger than 10 power 10 or k to power log k, this has no solution. So basically, any solution for this to happen, d has to be bigger than 10 power 10, and or also it has to be bigger than k power log k. So that conjecture is confirmed when d is less than 10 power 10. Another result in this direction is, okay, this equation has no solution when d is a number whose number of distinct prime factors is up to 4. So suppose d is a prime power product of 2 primes or 3 primes or 4 primes, then it can never be, there cannot be any solution. So if at all there is a solution, d should have at least 5 distinct prime divisors. Yeah, sure. Yeah.
Not exactly this, just like so. Do we have any results where we consider this mod prime? So we're using elliptic curve technique. Let's say,
Yeah.
you can also consider them over, like finite space.
Yes.
So then there should be some analog. If I view, okay, it's not possible
Mm.
z, but what about z mod z?
Yeah, so the thing is that, you see, when b is a number which is a quadratic residue mod p, then Yeah, so so I think modulo P is likely to have solutions for infinite and for like for a fixed K. So we should, it's likely to be it's likely that we'll be able to find numbers which has which gives a solution of this, because the right side is going to be when B is 1 or is square or quadratic residue mod P is going to be square. So it's likely to have solutions. So hmm.
Can we ask some interesting questions there and modifying the problem slightly?
So yeah, so maybe yeah, yes, yeah. Can you just?
So I was saying, okay, can we still ask some interesting questions mod P? I mean, P is that in one.
Yeah. So for example, say if D is a number divisible by P, and take any n not divisible by P, then it's going to be n power K. And K is even, it's going to be square mod P. So one can, one can keep, by making extra conditions, possibly one can come up with a more difficult way to ask. But in general, when K is even, already we have a solution. So, yeah, okay. Yeah, sorry. Yeah. Hmm. 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 Yeah. Yes. And also, so one thing is that, you see, it's divisible by every prime less than or equal to K. So you have to take P to be a larger prime, because otherwise it's going to be anyway 0. The left hand side will be anyway 0. So a weaker version of this conjecture is due to errors, which says that, okay, so we expect that there are no solutions when K is bigger than or 5, but can you just prove that there are only, K is bounded by an absolute constant. So so this equation implies that K is bounded by an absolute constant. Even if you can, the aim is to prove K is bounded less than or equal to 5, but uh, I'm not able to prove 5, okay, but can I prove that K is bounded by 10 power something or million, anything number, any finite constant. So there's a conjecture which is also still open. So there's a proof of this conjecture due to, by using ABC conjecture, we can give a proof. So it implies Erdős conjecture. A proof was given in my master's thesis and which also appeared in, so we gave a modified version of the proof of Granville. It's not completely new. So this was added in one of our paper, and it was published in JCNT 2016. So for those who doesn't know what is ABC conjecture, this ABC conjecture is considered one of the most difficult problems in number theory. So statement is very simple. For any given epsilon positive, there exists a computable constant k epsilon, which depends only on epsilon, such that whenever A, B, C are pairwise co-prime integers with A plus B equal to C, C is less than this constant times the radical. Radical means the product of primes dividing ABC to the power 1 plus epsilon. So this is, considered very difficult. In fact, in the last century, all the number theory field medal winners, their work follows from ABC conjecture. And Fermat's last theorem follows as a one-line proof from this ABC conjecture, the asymptotic Fermat. So we use another version of ABC conjecture due to Granville and Tucker, which looks a little bit more complicated, but it's an equivalent version where we start with any homogeneous polynomial which has no proportional linear factors. Then you can find a constant such that the product of prime divisors of this polynomial is bounded below by something in terms of m and n. So this is I'm not going to really go into it, but this is an equivalent version of ABC conjecture. So by using this, we can solve the Erdős problem. So there's only finitely many, like K is bounded by an absolute constant from here, but that is still conjectural. So now I look at another version of this this equation with in a different way. So still the address problem is open. Now can I say something more? So our aim to show that k is bounded by some absolute constant cannot. But what Sore and Teichmann showed is that k is bounded by an absolute constant depending on omega d, where omega d is the number of distinct prime divisors of d. So when d has said 10 prime divisors, k is bounded by some number depending on 10 and so on. So, but their result was not explicit. So it's kind of a, they found that, okay, there's some constant depending on number of distinct prime factors of d. So we gave I along with Sore gave an explicit version of this result by showing that if there's a solution to this, then k has to be bounded by 2 times omega d times 2 per omega d, where omega d is the number of distinct prime factors of d. So this is the result we have. So now I'm going to combine all of this with what we have. So if you fix d, k is bounded by a number which is 2 times omega d 2 power. So d is fixed, then omega d is fixed. Number of distinct prime divisors of d is fixed, so this number is fixed. So if d is fixed, this is just a polynomial. So yeah, so n like this, like x plus d, x plus k minus. If k is fixed, yeah, so if d is fixed, k is bounded. So take any k less than that number, then it becomes just a polynomial. Then Falting's theorem tells you that n is bounded in this case. So if you fix n and k and d, then this is just a polynomial square. Something times square is a polynomial, and so there are only finally many values of n which is given by Faltings. But the finiteness is not clear. Whether it says 0, 1, 2, 5 million, trillion, we have no idea. So bound is not explicit. It's something called an explicit bound. So can you make it more explicit? Can you give a exactly fixed bound? So regarding this, I did some work recently. So I have a preprint, but I have not really, submitted it. So this is a work I did recently. So what we saw is that if for a fixed, whenever n is bigger than k squared d squared by 40,000 minus kd, then this equation has no solution. In other words, this number has a prime divisor bigger than k to n odd power if n is bigger than this number. Okay, so all right, so that means, yeah, so from here, I can say the following, give the following corollary. If you fix d, this equation implies that n and k can be bounded explicitly. So once you fix d, everything can be fixed. So n is bounded, so k is bounded by this number, and n is bounded by, once k is bounded, d is fixed, so n is also bounded. So this is the first result in the direction where we're able to fix we're able to explicitly bound all the variables when one of them is fixed. Of course, earlier by Falting's on, we know some finite, but nothing was explicit, but I could make it completely explicit. Yeah, so it will give another result. No, not D, K. It was K. So yeah, it will give a different result. So, and D, I know that up to 10 power 10 there are no solutions. Now this already beyond 10 power 10. So this is the result in this direction. Now this condition n bigger than this can be dropped. You see, in this result, I have n is bigger than this number. This condition, you see, I want to have this with this has no solution. I want to have without this condition. So this can be dropped if we assume the conjecture on largest prime dividing. So if I know that this has a large prime divisor, I can drop this condition. So this is the following conjecture. So if whenever m and d are co-prime, suppose m is bigger than or equal to dk. So you have product of k consecutive terms of AP where the first term is bigger than or equal to dk. Then it has a prime factor bigger than dk by 200. So I'll tell, in fact, conjecturally, what we know is that it says always a last, conjecturally we know that there is a last prime bigger than some constant times dk. With some computation and known results, I make it explicit to show that it has a prime factor bigger than dk by 200. This is open and it implies the conjecture one. So basically, this conjecture implies that this has only finitely many solutions. Case bounded, like it has no solution. Conjecture one means it has no solutions. And definitely this result is true for d less than 400. One can show that this follows from earlier results. And it has some also consequence on other results. Yeah, square of the first term. So, yeah, so basically, I will be able to sense this. So basically, yeah, it was the square of this term. So now the question is that can a product of k consecutive integers has a large prime factor? Now let's come to this problem. So you know that product of k consecutive integers has a prime divisor bigger than k, and Sylvester was the first one to show that if the starting point is bigger than d plus k, then it has a prime factor bigger than k. So there was a generalization for d bigger than 1. So now can you make it much bigger? Can you have a product of k consecutive integers bigger than some s times k where n and k is bigger than 2? Soren-Tiedemann shows that product of 3 or more consecutive terms of an arithmetic progression has a prime divisor bigger than k unless ndk is 273. If you look at this 2 plus 7, 2 plus 2 into 7, this is 2 into 9 into 16. So the largest prime factor is 3. So it doesn't have a prime factor bigger than 3. And what Soren-Tiedemann says that for k bigger than or equal to 3, this is the only case where it doesn't have a prime factor bigger than 3, bigger than k. And I extended this result by showing that there's a prime factor bigger than 2k for d bigger than 2 except for some finitely many triples ndk which was explicitly given from her. So that means this product has a prime factor bigger than 2k whenever k is bigger than d is bigger than 2. So that implies that when d is less than or equal to 4, the previous conjecture, this has a prime factor bigger than dk by 200. So that's why we have the following theorem. If this conjecture holds, that is, if whenever m is bigger than dk, this product has prime factor bigger than 200, then this equation has no positive integer solutions in n, d, k, by. These are all, you should remember that here n, d, k, by, these are all variables with the condition that k is bigger than 5, b is square free, and largest prime factor of b is less than k. So everything is a variable. So and there are no solutions. This is all. So this is the which actually I have written it down, but because I was trying to extend this till whatever possible, then just submit it. But this is the result we have. So you see, I'm not going to give a proof of many results, but I just want to give a proof of this last result. That if you assume this, then this solution has no, this equation has no solution. This is pretty simple. I'll give a proof, and then that's the only proof. So every lecture should have some proof to be taken. So I'll give everything which is simple. Suppose conjecture 5 is true, and you're looking at this equation. Now take m to be n plus k by 2d. Then that means you start with somewhere in the middle after second half. Then you have this the k minus k by 2 consecutive terms of arithmetic progressions starting at m bigger than k by 2d, which is k minus k by 2d. So by the conjecture, this equation this largest, so largest prime factor of this number is bigger than largest prime factor of, is bigger than dk minus 1 by 400. Now, I'm going to assume that, I can assume that k is bigger than 100 because this equation has no solution when k is less than 100, less than or equal to 100. So since k is bigger than or equal to 100, this number is definitely bigger than k. So this, so largest prime factor of this number is bigger than k. So in fact, dk minus 1. So since since dk minus 1 by 400 is bigger than k, and I know that if there's a solution, means every prime bigger than k should divide to a square part. So that means the largest number and largest term n plus k minus 1 d should be divisible by the square of the largest prime, which is bigger than dk minus 1 by 400 square. And so which turns out that n is bigger than this d square k minus 1 square by 16,000, the 1,60,000 minus dk, which is bigger than dk. Because you see, I know that k is bigger than 100, and one can easily show that this number is bigger than, d is also bigger than 10 power 10. So clearly this number is bigger than dk. Yeah, these, yeah, this is bigger than 10 power 10, k is bigger than 100. So because of that, I get this. Now, so in all of these numbers, now d is bigger than 10, n is bigger than dk. So it has a prime factor bigger than dk by 200 by the conjecture. And then after that, now from here, if you take n plus k minus 1, this is p square. So this number is bigger than dk by 200. So that means, so this proves conjecture. So that means I have got n plus k minus 1, this dk by 200 whole square. Once this number is true, this equation has no solution. That's what I proved in one of the theorems. So now the assertion follows. So this is the theorem. If n is bigger than this, then this equation has no solution. So once the conjecture 5, it has a large prime factor, then this equation has no solution. That is proved. So in fact, this proof of theorem 6 is quite complicated. It requires a lot more ideas. I'm not able to give a proof here, but it requires a lot of things. It requires ideas from quadratic reciprocity argument, prime number theory estimates, a lot of combinatorial arguments. And there's something called linear forms in logarithms due to Alan. So Alan Becker has, like there's a work of Alan Becker on the linear forms in logarithm where you have you have this linear forms combining a logarithm with coefficients and trying to give a bound, or then simultaneous Pell's equations, and quite a lot of things are involved just to show this theorem. So, show this previous theorem, what to say. So this theorem, so I'm not able to give a proof here, but so this is the main work actually of that work, which I was trying to get. Oh, 3 dots. Yeah, thank you for yeah, 3 dots. Yes. All right. So now I come to the second. So I started with, you remember that I started with the initial question about can you have arithmetic progression consisting of just squares? So now we saw that up to 4. You cannot have 4 arithmetic progressions in 4 squares in an arithmetic progression. Then there are 2 questions. One is that given an, so I look at one problem. I look at the second problem. Now I look at second problem. So given an arithmetic progression of blank n, can you tell me how many squares are there? You see, if you take 1, 2, 3 up to n, you expect around root n squares, right? So now take any arithmetic progression, a plus q. So I'm from n d, I'm changing a q. So a is the starting point, q is the number, a and q are co-prime, and you're looking for the number of squares here. Yeah, so. Huh?
So is there anything known? We are working over q, but we can work over number field as well. That's the same thing.
So we're working over integers. So we can work over, of course, number fields. Yeah. So that No, yeah. So, in fact, I try to look at literature. There's nothing much, but it looks quite complicated. So, over integers, luckily we have. You see, the methods which were used to solve this, they use estimates for prime factors and other things. Over number fields, somehow we don't have those things. So, even finiteness part, I'm not sure how if we can prove it. So, in literature, there's no such result. You see, people talk about this. I'll tell you about general, like on the other problem which I'm going to consider, there's some version in the number fields case. But at least in the product here, there doesn't seem to be any result. So it may be interesting to have a look at it because how, but I have no idea how we can do it. Yeah. Because here really some properties of integers are, explicit properties of integers are used. Hmm. Okay, so now I look at this another problem. So you're looking at n-term AP and you're asking how many squares does it have? So, okay, just forget about it. So basically you just let Q and QA count the number of squares in this arithmetic progression. Now you take all possible arithmetic progressions of length n. So now, and you're counting the maximum number of possible squares in an arithmetic progression of length and you call it Qn. So Q, given capital N, Qn counts the maximum number, maximum number of squares in an arithmetic progression of length n. Now Fermat's result, recall Fermat's, what does it says? You cannot have four squares in an arithmetic progression. So now Q of 3, Q of 2 is 2. Q of 1 is 1. So there you have infinitely many 2-term AP which are squares. So Q of 2 is 2. Q of 3 is 3. But Fermat's result tells you that Q of 4 is actually 3. You cannot have 4 squares in AP. So now you take any n, you take multiples of 4. 4, 4, 4, 4. If 4 has 3, at most 3 squares, so Q of n is at most 3n by 4. So that's what I've written. Q of 1 is 1, Q of 2 is 2, Q of 3 is 3, Q of... Now Fermat will tell you that Q of 5 is also less than or equal to 4. Now I want to remark here, every square of an odd number is 1 mod 8, and if 3 doesn't divide, it's going to be 1 mod 3 also is going to 1 mod 24. Now I'm exhibiting a 5 times AP of 4 squares in an AP of 5. So, sorry, 1 plus 24 is a square, 1 plus 2 into 24 is a square, 1 plus 3 into 24 is not a square. This, so you have a 5, so 6 times AP with 1, 2, 3 squares, and one square. Yeah, I mean, thank you. 1, 2, 3, 4. 4 squares in the 6 times AP, and 4 squares in 5 times AP. So 49. If you start with 49, 49 plus 120, 49 plus 2 into 120, 49 plus 3 into 1. Except this, everywhere else is a square. So therefore, I'm giving a 5 term AP of which 4 are squares. And I know that Q of 5 is less than or equal to 4. So this tells you that Q of 5 is 4. Now I come to this, your question regarding the number fields. So Gonzalez, Jimenez, and Charles in 2013 proved that over quadratic fields, this sequence is this 5 times AP is the only quadratic. I mean, so Q square root of 409 is the only quadratic field having 5 squares in arithmetic progression. So over quadratic fields, you can have Q of n to be n. I mean, for n equal to 5, and here, this is the, in this quadratic fields, all of them are squares. So now, okay, so I've defined what is Qn. So remember, Qn means there are n terms AP, then you're looking at the maximum possible squares in that AP. Now, there's a conjecture, yeah? No, you see, every square is one mod n, right? But of course, when 3 doesn't divide, that the square is 24. So that's why I said almost. It's not all. So there's a conjecture of Erdős. So Erdős conjecture that number of squares, maximum number of squares should not be a multiple of n, but it should be much smaller than n. Or small o notation means that this q of n by capital N should goes to 0 when n goes to infinity. So Semeredi proved this result in 1975. So, he got a Nobel Prize work for his, many work, including the existence of arithmetic progression in a given set. So, by using some of the ideas and results in this work on existence of arithmetic progression set, he proved that the maximum number of squares should be something is much smaller than n. So the proof is quite difficult. It's not easy, but the Qn has to be very small compared to n. Now, next question is that how big or how small is it? So then there's this recent work of, okay, I didn't write the year, 2012, 13. So there's this work of Bomberry, Granville, and Pins where they shows that number of squares can be at most 2 by n to the power 2 by 3 for any n. So make up to n, the at most n to the power 2 by 3 squares possible. And later on, Bomberry and Janier, they extended, they improved this power to n to, so up to n, you can expect about 3 power 5. Basically, it says that when n goes to infinity, maximum number of squares should not go beyond n power 3 by 5. So then we come to the conjecture of Rudin. So Rudin made the following conjecture. So you see, if you have n consecutive integers, there is square root n square. So he said that it should also happen similarly for arithmetic progressions of length n. So this is conjecture. So up to n, you should be able to expect around the square root of n squares. So there's a strong Rudin conjecture which tells you that the maximum number of squares should come from the sequence 1, 1 plus 24, 1 plus 2 into 24, 1 plus 3 into 24, and so on. So that is the expected. So so in this case, the number of squares will be square root of 8 by 3n plus some constant. It's the Rudin of principle, Walter Rudin, yes, Walter Rudin. So of course, this conjecture is open. So you see, n equal to 5, this is not correct. Because 49, 120, that is 49 plus 120, that's the thing. But after 5, everything else should come, the maximum number of squares come from the arithmetic progression 1, 1 plus 24, and so on. Now, Gonzalez, Jimenez, and Charles, they verify this conjecture when capital N is less than 52. So basically, they prove that when the number of length of the arithmetic progression is up to 52, the maximum number of squares come from this arithmetic progression starting at 1 and common difference 24. So now, me along with my former student who is now a faculty in US, Pranavesh Das, we were looking at this problem. So we were able to get some new insights. So it's still ongoing work, so not. So I want to tell you. So basically, we could connect it to quadratic reciprocity and certain ideas. So we're looking for squares in the form a plus q, a plus 2q. So we can start with assuming that the initial starting point is a is a square, and a is either odd number or a number divisible by q. So then by looking at the fact that, okay, so given any q which is odd or or q naught which is q of the form q by 2 if a divides q, let's count the number of solutions of this equation. X square is a square mod q naught. So number of solutions of this equation is given by modulo q naught is given by this a1, a2, a to the power omega. Remember that omega of q naught is the number of distinct prime divisors of q naught. For example, when q naught is a prime power, there are exactly 2 solutions modulo a prime power of this equation. X is congruent to a, x is congruent to x is equal to a and x is equal to q naught minus a. So when q naught is a like composed of omega prime, then there are actually 2 power omega prime solutions modulo q naught. So basically A1 plus this one should be Q naught, A2 plus, before that will be Q naught and so on. So whatever number by Q by 2, before Q by 2, you should have something Q, I mean if A is a solution, I mean some AI is a solution, then Q naught minus AI is another solution. So we have this many solutions. So what we are able to show is that Rudin's conjecture is equivalent to showing that 2 times ai square minus aj square by q is bigger than I minus a square. Whenever I minus a is at least 6, or ijn runs between 1 and 2 power q naught. And in this process, we are able to prove it when q has less number of prime factors. So when q has up to 5 prime factors, we are able to show that the Rudin's conjecture is true. So like here, we're looking at it in a different, so Rudin's conjecture is a given n, we expect square root of n, I mean at most square root of n, I mean like the largest number of prime factors should come from here. So we're not able to prove for all q, but up to when q is composed of 1, 2, 3 or 5 prime factors, we are able to prove it. So we're trying to actually, still work in progress, we're trying to see how far we can go. So this is the thing. The main thing is that we saw to prove Rudin's conjecture, to show it's showing equivalent to showing this, and from here we could get this by some approach. Yeah, I'm dropping in 1-2 minutes. So, thank you. So basically, this is the theorem we have. So first theorem, I mean, one of the theorem is that, yeah, whenever q is odd or q is even number not divisible by 24, so the maximum number of squares is bounded by this. This is the theorem. So a strong Rudin conjecture is equivalent to proving that for any q, I mean, if you look at arithmetic progressions with common difference dividing by 24, then that should be number of squares in that sequence should be always less than number of squares in an arithmetic progression of length and whose common difference is 24. So we gave another equivalent version of proving the Rudin's conjecture in this. So and here, of course, we're still trying to see like when the common difference is composed of 5 primes or only, and not only that, 24 has to divide the common difference. This is what we have, and so that is what we have so far. We're still, that is a work in progress. So here I want to stop by telling you about some related problems and comments. You see, I've considered product being a square or terms being a square. So you can, instead of squares, you can give any power like cubes, 4, 5, any power. So there's some number of known results and problems in the direction. I'm not going to go into it. But the thing is that when you have cube and higher powers, things are easy. So you know that x squared plus y squared equals z squared. Pythagorean triplet has many, infinitely many solutions. But x cube plus y cube equals z cube has no solution. So you see, when powers are higher, so it has some sort of a nice property. So they're a bit different, but in case of squares, things are a little bit different. So and it seems that squares is more difficult to handle than other powers. That's why we actually look at the squares. It has some nice property from other parts, quadratic reciprocity, others. But on the other hand, like it doesn't have some nice properties coming from other powers. So it requires a different approach to handle, and that's what we are doing here. So with that, let me stop here. Thank you.
Yeah, no question, but thanks.
Okay. Yeah. No, these are all positive integers, right? Yeah, so you see, rational numbers can be turned into integers by dividing with the suitable denominator. So you'll get, I mean, you can get a result once you have 4 integers. No, can you, sorry, can you? Oh yeah, actually, yeah, so that will be interesting. So you see that, uh, like another problems that we see, the conjecture is that NQA is bigger, less than this, right? Now we can ask, I mean, or what is the probability that the given Q, I mean, how, when is satisfied, or what is the up to, I mean, up to capital X, so how many Q satisfies this? So basically it should satisfy for all, but I mean, like, can you give a probabilistic by, I mean, so some sort of, our aim is so the probability is 1, but at least some positive propose, tending to, so yeah, instead of, I mean, can you give some kind of a lower bound that is close to 1 or at least some positive? No, actually, that is very difficult to see. You see, squares can behave in a very different way. So that's why it's difficult to handle because I don't know. I mean, like if you take an arithmetic progression, squares can start at here, here. I mean, they can always come and go for back and forth. So yeah, it's like it looks random. So we are not able to really control where it's coming. So that's why it's difficult. But as you said, it might be interesting to sort of see, like, set up the probability that given Q up to a given density or density of Q for which this is true, up to capital X number of set of Q for which this is true. So if you can give a upper bound or lower bound, that may be interesting. Positive lower bound. Yeah. Well, no, actually, it doesn't seem to have any relation with that, but. Huh, huh. So that, of course, if I can say something, I'll be very happy, of course. If I can see some connection or if it gives something, but yeah, unfortunately, I don't know. Yeah, so here, prime, no, so in the first part, the first problem, I'm playing with primes. Here, I'm, yeah, of course, primes are involved, but more than that, I'm playing with the, see, this quadrant, this problem, you see, I was struggling for quite some, I mean, things I was trying to solve it. It looks extremely, I mean, doable. I mean, of course, but then when I really try to prove it, uh, I mean, like a lot of things were coming in. So when Q is up to 5 primes, we're able to somehow manage it. So when going beyond 6 becomes hard.